SwayamPrabha. Digital India. Educated India.
Hello everyone. Now we will continue with the fibers used for protective textiles. So, we will start with stainless steel fiber. So, first let us see the structural characteristics of stainless steel fiber. So, you can see here the stainless steel fibers are fine high performance strand from specialty alloy. So, we it is the fiber stainless steel fibers are very you can spin stainless steel fiber in very fine micron, and these fibers are very flexible in nature, and the stainless steel fibers comes from in the shape of straight, hooked or crimped form. So, we can create stainless steel fibers in different forms, and for spinning we typically require little bit crimped fiber, that is blending with other fibers like viscose or polyester. We can blend the stainless steel staple fiber also, and the surface of these fibers may be smooth or rough depending on our requirement. We can create different types of fibers, and usually made by bundle drawing, where wires of bundle of wires are drawn and annealed. So, at a different in bundle form we get. So, we ultimately we can create the multi-filament fiber by drawing. Now, if we see the chemical characteristics of stainless steel fiber. So, this is the chemical structure typically for stainless steel fiber. So, here you can see high corrosion resistance due to their chromium content. Here there will be chromium is actually mixed with that. So, it is due to the chromium content, these are corrosion resistant, excellent oxidation resistant are at elevated temperature. So, these are resistant to oxidation. So, for long term application we can use this stainless steel fiber, where it does not corrode or oxidize. So, resistant to aggressive chemicals and atmosphere. So, for external application we can use this fiber for specific application. So, non-magnetic. So, here we can see that stainless steel fibers are non-magnetic, or sometimes it may be low magnetic properties due to their face centered cube, actually FCC crystal structure. So, due to that it is not magnetic, stabilized by elements like nickel. Okay. So, these are the different chemical characteristics of stainless steel fiber, and we can use this fiber in a particular applications where this type of corrosion or oxidation or aggressive chemicals or atmospheric threats are there. Okay. And where we need non-magnetic material, non-magnetic metal if we need. So, this type of application we can use this stainless steel fiber. Now, if we see the thermal characteristics of stainless steel fibers are stainless steel fibers can be withstand continuous temperature of about 1200 to 1300 degree Celsius. So, for very high temperature application we can use this stainless steel fiber without any degradation. So, a thermal conductivity you can see at room temperature 14 to 16 at room temperature. If we elevate the temperature, the conductivity can be increased. So, at around 500 degrees Celsius, the thermal conductivity becomes 20 to 22 at that range. So, thermal expansion coefficient is 15 to 19 10 to the power minus 6 per degree Celsius. So, per degree Celsius this is a very low, which helps absorb thermal cycling stage. So, thermal expansion is low. So, it actually thermal cycles, it can absorb very easily, okay, where thermal changes are there, temperature changes are there. In those applications we can very well use this stainless steel fiber, and high fracture toughness, okay, and heat stability gives stainless steel fiber strong resistance to the thermal shock and cycle. So, at different changing temperature, at those conditions and high temperature where thermal shocks are there. So, it is highly resistant to this conditions because of the low thermal expansion coefficient. Specific heat capacity is 0.46 to 0.5 at room temperature, and as we increase the temperature, that specific heat capacity can be changed. Now, our next is the mechanical characteristics of stainless steel fiber. If we see, the incorporation of stainless steel fiber increases the elastic modulus of material. So, it has got high elastic modulus. So, for any composite material, if we need to increase the elastic modulus, we can use stainless steel fiber. These fibers are ductile with up to 4.5% failure strength. So, it is not that it is brittle. So, for any material it can absorb some energy. So, it has the capability, it is high strength and it absorbs the energy. So, that means its toughness is good. So, 4.5% breaking strain it is there, and it resists brittle failure and allowing large deformation. So, that is why I already explained that it absorbs energy. So, it bridges cracks in brittle material. So, we can actually blend with or brittle matrix if we use. So, in those cases it can actually bridge the crack. So, enhance the post crack strength, flexural capacity and the impact or fatigue resistance. So, as we have discussed earlier, so for a different, as like a different temperature difference it can be used. Even for repeated mechanical shock we can use this fiber for reinforcement, and particularly for brittle matrices. And this stainless steel fiber lets the composite maintain ultimate strength after fatigue cycle. So, if we use stainless steel fiber for as a reinforcement for any composite like thermoset composite or thermoplastic. So, it will keep the strength intact after repeated cycle, that is through flexural stiffness may be declined. So, it is a tensile strength will be tensile stress may be maintained, but sometime the flexural stiffness may decline with the with repeated fatigue cycling. So, adding stainless steel fiber boost toughness, energy absorption, long term durability under stress cycle. So, we can use where this stainless steel fiber where repeated loading for long term repeated loading cases are there. So, that in that case the stainless steel fibers can increase and it will increase the toughness. So, stainless steel fiber integrate well into the matrices like concrete, enhancing the mechanical reinforcement and performance. So, for concrete the we can use this stainless steel fiber for reinforcement, because it has got very good cohesion with the concrete and it increases the performance. So, what are the applications? Let us see. Refractory lining for as reinforcing material, concrete reinforcement as we have already mentioned, filtration system, high temperature filtration system we can use this fiber because of low thermal expansion, the pore size will not get changed, it will because of the low thermal expansion. So, for very high temperature filtration we can use gaseous filtration, we can use this stainless steel fiber. So, automotive and aerospace components we can use this fiber for automotive and aerospace component due to its high fracture resistance and also very good toughness. So, protective and fireproof fabric because of its very high melting point we can use for protective fabrics, or in some cases we can use for fireproof fabric reinforcement we can use. Heat resistant parts where we can use this stainless steel fiber in those areas where the high heat resistance are required. So, for those application we can use stainless steel fiber, and glass industries where high temperature applications are boiling are there. So, those industries we can use stainless steel fibers component. Marine construction and infrastructure because of its low chemical reactivity, it does not actually degrade with the external environment, or it is not reacted with the saline water, or so for all these application external application we can use stainless steel fiber. Medical, food, clean room industries we can use because it does not react easily. Electromagnetic shielding because of its high electrical conductivity. For electromagnetic shielding it is widely used this stainless steel fiber for protecting us from any electromagnetic wave. So, after stainless steel fiber, let us discuss the carbon fiber. Carbon fiber is very commonly used for protective application, and also in composite or technical application we use this carbon fiber. Now, let us see the structure. What is the structure of carbon fiber? We can see the carbon fiber, this is the structure here, and this carbon fiber is composed of primarily the thin strand of atoms tightly bond together in a crystalline structure. So, these are the very thin strand, thin strand, okay, and forming graphite plane aligned along the axis. So, this you can see, this is the axis, this is the axis, and here these are the graphitic planes, these are the graphitic planes, and they are aligned along the axis. This is along the axis of fiber, okay, along this plane. So, multiple planes are there arranged. So, carbon fibers 5 to 10 micron in diameter, offering high surface area for excellent bonding. So, it is you can get the carbon fiber with a very low diameter 5 to 10 micron, and as the diameter is less. So, we can get higher surface area, and if we get higher surface area. So, the bonding maybe that is with the some matrices. So, if we use it as a reinforcing material, so it will get very good high surface for excellent bonding. Now, if we see the chemical structure, carbon chemically you can see it is a 93 to 99% content is carbon content, and bonded like graphite like crystalline structure. So, majority almost 99% carbon content. Okay. Now, carbon atoms with the graphene layer are linked primarily by the strong sp2 bond, covalent bonds. So, they are linked with the covalent bonds. Carbon fibers may have 1 to 2 that microvolt, okay, and defect zone with the microfibers shaping unique property. So, and carbon fibers are often surface treated to improve bonding with polymer matrices. So, we can treat the carbon fiber for to have some surface treatment, basically with the polymer, the cohesion with the polymer. In if we use as a reinforcing material with the some polymeric material like polypropylene or some other matrices. So, the bonding may be improved by some surface treatment. There are different types of surface treatments are available, which improves the interface between the polymer matrix and carbon fiber. So, in the carbon fiber, when it is treated at the surface treatment, that is interface is created, and which actually helps in better bonding with the matrices. So, let us see the thermal characteristics of carbon fiber. So, it conducts heat much better along its axis than across this. So, as we have seen this I will come back. So, these crystalline structures, okay, the graphite planes are aligned along the axis. So, the heat conductivity along the axis will be much better than across the So, this is the fiber and here the graphite planes are aligned along the axis. So, heat conductivity will be better in case of in the lengthwise direction along the axis than across the axis. This also depends on the orientation, porosity and density. So, if we increase the density or porosity is reduced, so the fiber orientation. So, this will we can change the conductivity. This is true for other fibers also. Carbon fiber exhibits low or even negative coefficient of thermal expansion. So, this is very good, it does not expand or sometime it contracts basically. So, thermal expansion is not there. So, even if it is there very low, this maintains dimensional stability at high temperature due to low thermal expansion and strong covalent bonds. So, for very high temperature application we can use this carbon fiber. Now, let us see the mechanical characteristics. It has very high tensile strength, typically we can see 3500 to 5400 megapascal, very high tensile strength. So, for high strength application we must use this carbon fiber. Modulus of elasticity of carbon fibers typically 230 to 294, around 300 gigapascal, which is very high, and it does not have any yield point. Okay. So, it behaves like elastic material. So, here that means if the applications where we need we do not need any yielding. So, for this high strength application, so it behaves like elastic material. So, it will actually after removal of heat mechanical load, the material will come back to its initial position. So, if you see the stress strain curve, strength. So, you will see it has got perfect, almost perfect elasticity. High tensile and compressive strength. So, it has got a very high compressive strength also. Hardness value, because its toughness is it's very hard. So, shore hardness typically 85 to 90. Unidirectional fiber offer high axial strength, stiffness, oven, it can be converted to oven fabric. So, we can create a fabric called multidirectional fabric with high strength. So, let us see the applications. There are very wide applications are there where high strength and at high temperature are required. So, aerospace and aviation here widely used the carbon fiber for reinforcement. Automotive and motor sports. So, their carbon fibers are used lightweight, highly strong like for motor sports bike. So, there the components are carbon fiber reinforced composites. Industrial automation and robotics, where we need high strength at lower mass. So, that this type of application we can use. renewable energy, where in wind mill that the blade we can use the carbon fiber for reinforcement. Sports and recreation, for many, like your tennis racket is reinforced by carbon fiber, or maybe sports bike. So, their carbon fiber reinforcement to have very light weight. Construction and infrastructure, there we can use carbon fiber. Electronics, definitely we can use for maybe electromagnetic shielding, and there are many applications we can use, and medical and other applications. So, like automotive and sports recreation, the helmet reinforcement. So, there we can use carbon fiber. So, next fiber is ceramic fiber. So, it is different, little bit different from the glass fiber we have discussed. So, we can see here. So, let us see the structure of ceramic fiber. So, ceramic fibers are made from oxide ceramics. So, aluminum oxide, silicon dioxide, okay. This type of different chemicals we use, different oxide ceramics are there. These are the aluminum oxide, silicon dioxide. So, these are the oxide ceramics, and also organic ceramics are there, and also non-oxide ceramics like silicon carbide. These are not the oxide ceramics. Okay. So, oxide ceramic fibers usually have polycrystalline microstructure with fine crystalline like aluminum and mullite. So, this is oxide ceramic, and non-oxide ceramic like SiC possess more uniform crystalline structure with high modulus. So, if we want the more uniform crystalline and high modulus, in that case we should go for non-oxide ceramic fiber. It is actually amorphous fiber or polycrystalline fibers based on their microstructure. So, they can be characterized, okay, in two ways. Now, chemical structure of ceramic, their chemical characteristics. So, they are highly resistant to chemical attack, including acid and alkaline. So, the applications where chances of threat of acid or alkaline, the protection we require, on those applications we can use ceramic fiber. Excellent resistance to oxidation, it does not get oxidized easily, and corrosion at high temperature. Chemically inert under most industrial processing conditions. High temperature chemical stability, this which allows the harsh environment like furnaces, reactors. So, basically this is a very good candidate for the extreme environmental condition, where high temperature is there, high the concentrated acidic chances of acid attack or alkaline conditions are there, even oxidation. So, all this type of specialty applications we can use the ceramic fiber, like it resists corrosion from molten metal. So, it does not corrode easily. If you see the thermal characteristics, so it is actually it keeps its continuous strength, okay, and performance for extreme temperature with continuous use up to 1600 degree Celsius. So, very high temperature application where the temperatures are around more than 1500 degree Celsius application, and it can retain its strength and performance. It has low thermal conductivity, typically around 0.1 to 0.16 watt per meter Kelvin, low heat storage capacity allowing rapid heating or cooling cycle. So, that for furnace and all these application we can use ceramic fiber for reinforcement. It resists thermal shock, that means heating cooling cycle, actually it gets heated quickly and cools down quickly. So, we can use where thermal shock is there, it resists the thermal shock because it gets heated quickly. So, thermal shock is not there and staying stable under temperature changes and avoiding crack. So, that is very very important characteristics for high temperature application, and it retains thermal properties even in aggressive condition, okay, or oxidizing condition. Now, let us see the mechanical characteristics of ceramic fiber. High strength, but it is brittle. So, that is the bending strength is poor. So, it does not elongation is very low. So, low toughness, because if you see that this is the strain, so if you see the glass fiber, this is the elongation at break will be very very low, but strength is very high. That is why its energy absorption during the stress application when the load is applied. So, energy absorption is very low. So, it behaves like a brittle material. Retain strength at elevated temperature. So, as we have discussed, it does not, it is it can withstand temperature of prolonged temperature of more than 1500 degree Celsius. So, it will retain strength, good creep resistant. So, it does not creep easily at when the at constant load. So, for those applications we can use this ceramic fiber, sensitive to surface flaw and micro crack. So, while production, so if there is any micro crack or surface defects are there, then the mechanical characteristics will drop drastically. Now, if we see the applications, so most of the applications we use where the high temperature conditions are there. So, thermal insulation in furnace, kiln and reactors. So, in those applications very high temperatures are conditions are there. So, for those applications we can use this ceramic fiber, heat shield or fire protection, that heat shield jacket. So, that we can use for any application where very high temperature conditions are there. So, aerospace component engine insulation, tiles. So, these applications are there, high temperature gasket and seals, there we can use the ceramic fibers, filtration in molten metal and hot gases. So, this is very unique applications, molten metal filtration or in hot gas filtration, there we can use the ceramic fiber. Now, coming to the natural fibers, as we have discussed, the high performance fibers are very widely used for human protection. Not always the high performance fibers are required, but we can also use to some extent natural fiber for maybe cost consideration is there, where threat is not that much, or we can use as a separate layer in a, like in fire protective clothing, we can use the cotton fabric at the inner layer, innermost layer for comfort application. So, not only this high performance, natural fibers are also used sometime. So, the fiber structures are two types, one is basically staple fiber, another is continuous fiber. So, natural fibers, if we see here, the staple fibers are short fiber length, few millimeter to few centimeter, irregular and discontinuous structure, because these are the natural fibers. So, they are grown in nature. So, there will be irregularity, and as this is staple fiber, they are discontinuous in structure like cotton. And if we want to form a continuous strand in the yarn form, so there we need twisting, or we have to impart crimp if it is synthetic fiber, natural synthetic the regenerated natural fiber. So, crimp is required, and in cotton there is a natural crimp in the form of convolution is there. In wool it has got natural crimp, rougher surface than filament. So, as these are grown naturally, the surfaces are rough and produces bulkier, softer and warmer fabric. So, natural basically for continuous filament fabric, they are not bulkier, and if we that continuous filament yarn are not bulkier because of their consistent diameter or unique uniform in the single strand or single strand put together, and there you can create a thread of continuous filament with less gap in between. Okay. Their gap will be less, but in case of staple fiber yarn, as these are they are staple fiber, they are discontinuous fiber and they are put together with the help of twist, and also crimp is required for high cohesion. That is why this produces bulkier and softer and warmer fabric, because why is it warmer? Because in staple fiber yarn the air pockets are there, and this air pocket the entrapped air are actually with a high thermal resistance. So, they are they produce warmer fabric than the filament, continuous filament fabric. Cotton, wool, flax. So, these are the examples of natural staple fiber. Now, if you see the chemical structure of cotton, it is a cellulosic fiber. So, cotton is one very common natural staple fiber. Reactivity varies with the fiber type. natural or synthetic fiber, good dye and finish absorption because of their wedge bonds, they can absorb finishes, okay, or dye. This is susceptible to the degradation by heat, UV or chemicals. So, they are easily degraded by heat or UV or different chemicals, it is degraded. Some of the natural fibers, they show resistant to acid. Now, thermal characteristics, limited heat resistance varies by fiber type, like cotton will have different thermal resistance, heat resistance than wool. So, depending on the chemical structure, natural fibers may, like wool, cotton, may char or decompose at high temperature. That is the problem of natural fibers. That is why we cannot use these fibers for high temperature application. Like ceramic, we have discussed, they are continuous high temperature application we can do, but this natural fiber we cannot use in high temperature application. Now, synthetic fibers like polyester, nylon, the staple fibers can melt or shrink under heat. This which provides insulation, that is because of the staple fibers they create, as I have mentioned, they air pockets, the staple fiber yarn, and that they give some insulation. Mechanical characteristics of this, the short length reduces the strength, tensile strength component of continuous compared to continuous filament. So, due to the shorter length, the yarn strength will be lower than the continuous filament because of the various factors like fiber to fiber friction, fiber alignment towards the axis. So, in continuous filament yarn, all the filaments are aligned to the load direction, but in case of staple fiber yarn, you can see here the staple fiber yarns are, the fibers are aligned at angle theta. So, when the load is applied, so load is applied, so the fibers component, fiber is actually carrying the load, that is L cos theta. So, that is the component which fiber is carrying. So, that means the load carrying capacity of fiber is low, moderate elasticity, and it is flexible, soft, bulky, giving good fabric loft and resilience. So, if we need a fabric with like a protective clothing with soft feeling, there we must use the staple fiber. So, for any protective textile which is in touch with the body, inner garment, inner layer, there we can use the staple fiber fabric. Strength and durability varies with the fiber type. If it is natural fiber, strength will be lower than the synthetic fiber. So, if we see the application, the spinning into yarn for clothing and textiles, home textiles, bedding, carpets, upholstery, bedding, carpets. So, for different applications. So, in non-ovens, insulation, filter, wipes we can use in the form of non-ovens. blended fabrics for enhanced property. So, for this upholstery, carpet and bedding. So, in this applications we can use the blended staple fiber to have higher strength, like if we need absorption for that those case we need say cotton, but if we want to enhance the strength, so we can blend with the polyester fiber. Craft and industrial uses, felt, paddings. Structural characteristics of these fibers, like cotton fiber structural characteristics are there. So, it is a natural origin. So, it is a cellulosic fiber oriented in the oriented form, and it is actually obtained from the sheet of hairs of cotton plant. Okay. So, natural cellulose in a certain orientation, and we obtain it from the cotton plant, and it is a ribbon like twisted, that is convolution is there. Convoluted structure helps in interfiber cohesion, that is a as I have mentioned, it is like a twist crimp. Length is typically 10 millimeter to 60 millimeter for different varieties of cottons are there. Diameter 12 to 20 micron, and cross section is like a kidney shape. This is a like or bean shape, becoming flattened when dried. So, in case if we swell it, this is the lumen, if we swell it, it will be like rod like structure, and when it is dry, this will be like bean type shape. So, as the fiber become dry, so the lumen collapse and it forms the bean type shape. So, here you can see it is majority of the content is cellulose, 95% around, and minor is a you can see the wax, protein and pectins, some little bit amount. So, chemical characteristics, you can see the structure of cotton fiber, which is cellulose swells in water due to its wedge group. So, as the wedge group is there, it forms with the bond with the water and it swells, reacts with alkali. So, with say mercerization with NaOH improves the strength and luster. Stable to dilute acid at room temperature, but degrade at hot concentrated acid. So, at normal light diluted acid, it is stable. It is actually affected by the oxidizing agent like bleaching with NaOHCl and H2O2. It can degrade the fiber and it reduces the strength, and combustion burn readily with the like a paper like smell. So, cellulose base, as it is cellulose base, it burns easily and it releases the smell like paper. So, it is resistant to organic solvent. So, for normal organic solvent we can treat this cotton product, it will not react, it is resistant. So, thermal characteristics if you see here, So, it has not does not have any true melting point, but it decomposes at high temperature okay, before melting. So, it does not have true melting point, and it starts decomposing at around 250 degrees Celsius, 240 to 260 degrees Celsius, and rapid degradation takes place above 300 degrees Celsius. So, at high temperature cotton fiber starts decomposing about 407 to 410, burns readily with paper like smell. So, at high temperature, so at above 400 degrees Celsius it starts burning. It is highly insulating. So, low thermal conductivity makes a good thermal insulator when dry. So, it is due to air entrapment in convolution. So, that is why it due to the convoluted structure. So, this type of convoluted structure, in this convolution the air entrapments are there. So, when we produce fabric or yarn and fabric, so large amount of air is being entrapped. So, that makes the cotton fabric highly insulating. So, particularly in dry condition. Regain up to 7 to 8% moisture. So, it moisture regain is typically is 8% standard, and if we change the humidity, with the increase in humidity moisture regain also increases. It can withstand ironing up to 200 to 220 degrees Celsius. So, at high temperature we can do ironing depending on the finish, and prolonged exposure can scorch. So, prolonged exposure that can start degrading. So, moderate thermal stability and prolonged heating yellow and weaken the fiber due to the oxidation of cellulose. So, if we keep the cotton fabric at high temperature for long time, and it will start degrading okay, and there will be yellowing in the fiber. So, this is due to the cellulose starts oxidizing, and if you see the mechanical characteristics of cotton fiber. So, tensile strength is when it can increase about 10 to 20% when wet due to the cellulose swelling and better hydrogen bonding. So, cotton has got one unique characteristics of that it in most of the fibers, if we see almost all the fibers, they either they are not affected by the moisture, or most of the fiber their tensile strength drops when it is wet, but cotton has got unique characteristic, that is it tensile strength increases by 10 to 20% when it is wet, and this is due to swelling of cellulose and better hydrogen bonding. Elongation at break, it is relatively low, around 7 to 10% elongation at break. Poor elastic recovery. So, that is the problem with the cotton. So, we cannot use at high stress application or even repeated loading application, the cotton will perform poorly, and durability is strong and tough fibers with good wear resistance. abrasion resistance is moderate. Now, we can if we blend with some other fibers, so that wear resistance can be improved. It is moderately flexible. Now, the applications are textile and apparel applications are there, like denim, t-shirts, shirts, trousers there, home furnishing, upholstery, okay, and carpet, rugs, industrial canvases. So, canvases, tarpaulin, tents, we use this cotton fiber, medical textiles, medical bandage, cotton wool, gauze, surgical dressing. So, this actually the some protective textile we can use this cotton fiber for its comfort characteristics, and also we can treat with antimicrobial treatment for medical application. Blend and specialized fabrics blended with polyester, nylon or elastane to improve wrinkle resistance and strength. Now, another staple fiber which is wool fiber. Now, the structural characteristics of wool fiber, if we see here, it is a natural protein fiber obtained from fleece of sheep and similar animals. So, it is basically a protein fiber, mainly keratin protein about 97% with small amount of lipid and minerals. So, mainly it is a keratin, roughly oval to circular. So, wool fiber, the as although it is a natural fiber, its actually cross section is approximately circular. That is why wool fiber is the fiber which is a natural fiber, which is expressed, the fineness is expressed in terms of micron. This is the only fiber, natural fiber, where we express its fineness in terms of micron diameter. Okay. So, due to its typically close to circular structure cross section, and it is covered with scales. Okay. So, that overlaps like roof tiles. So, if we see the surface of wool fiber, this type of scales are there like roof tiles, natural waviness due to bilateral cortex. So, it has got natural waviness, natural creams are there. Okay. Now, chemical characteristics of wool. If we see the chemical characteristics here, its wool is made of alpha keratin fiber, a fibrous protein. So, alpha keratin is mainly as we have discussed earlier, 97% of keratin. So, it is basically alpha keratin fiber, and which is built from the amino acid, especially SS and disulfide bond. So, sulfur content is there. So, you can see here. So, it is a disulfide bond which gives strength, elasticity and resilience. It contains peptide bond, CONH bond linked amino acid. So, COH bonds linked amino acid is there. As it is mainly acid protein fiber. So, it is it contains the amino acid. So, it is sensitive to alkali, even in mild NaOH it damages, it breaks the peptide bonds. So, that with the alkaline it reacts. it is fairly resistant to weak acid, commonly treated for acid dye. Okay. So, we can use the acid dye. Okay. It is so commonly weak acids commonly treated with acid dye. So, susceptible to oxidizing agent. So, bleached weakens the and dissolve the wick. So, it is oxidizing agent, it reacts, resistant to organic solvent, acetone, alcohol. Now, the thermal characteristics of wool. So, it has like cotton, it has got no true melting point, but again it decomposes before melting because of its protein base, and it begins degradation around 160 to 270 degrees Celsius and severe decomposes at 230 degrees Celsius. So, cotton has got little bit higher degradation temperature than wool. Ignition point here it is a 570 to 600 degrees Celsius, burned slowly with smell like a hair due to the keratin content, like hair burning smell will be there. Higher heat causes yellowing, weakening and loss of strength like cotton fiber. Wool absorbs about 30% moisture without feeling wet. So, it has got very high absorption capacity, still feel warmer even when it is damp. So, this is basically when the one unique characteristic of wool fiber is that it is a heat of absorption. When it absorbs heat moisture, it releases heat. So, that is why wool is very good material for cold country. A person when in the from dry environment at the room inside the room, when he comes out where the humidity is very high, snowing is there. So, instead of getting cooled, wool will start releasing the heat. So, in the damp condition even the person will feel warm, that is the unique characteristics. And the crimp structure in dry condition, the crimp structure traps air, providing excellent insulation against heat and cold. So, in for extreme cold protective clothing or even extreme heat protective molten metal protection, we use wool fiber, that we will discuss in detail. Naturally flame resistant, it burns slowly, self extinguished when the flame is removed. So, it does not get fire easily. Thermal conductivity is low, and mechanical characteristics, strength decreases when it wet, like in cotton it is just reverse. High extensibility 25 to 30%, 35% when dry, and even in wet condition extensibility is much higher, around 50%. Wool fibers return to their original length after stretching due to alpha keratin. So, that is the unique nature of wool fiber. So, when it is a like load elongation, this is the load elongation curve. When it is loading, after its release, the wool fiber will come back to its position normally due to the alpha keratin coil. So, it is a springy nature, high resistance to creasing, recovers shape after compression, So, that is why crease recovery is good, abrasion resistance is moderate, and natural crimp increases the elasticity of wool fiber. So, it works it extends easily, it is and that is why it has work of rupture is very high. So, if you see the applications, it is used for textile and apparel, suits, coats, jacket, trousers, in home furnishing, carpet, rugs, mats, industrial uses, sound and thermal insulation. So, for protecting us from the noise, so that human protection we can use sound and thermal insulation and fire resistant fabric. So, it does not get fire easily. Specialized use like military and outdoor wear, and medical and technical applications, cosmetic, skin care or absorbent pad. So, all these there are these are the all the applications. So, we will stop here, and next session we will start with another natural fiber, which is natural staple fiber, which is flax fiber. Thank you.